Hello, welcome and thanks for tuning in today. The paper I'm presenting is about front-running protection or fairness in blockchains, which has become a bit of an important topic lately. And the reason why it's getting more and more important is the price we pay for decentralization. So the nice thing in decentralization is I don't need to trust an individual party anymore. The price is I now open up my protocol over a worldwide distribution, so individual validators, links, internals are getting much more exposed. In the last 30 plus years, we got a lot of experience how to handle this in terms of creating consistency and agreeing on the order of events, which is essentially what a blockchain does. But very little work has been done on what a good order actually is, and it is in most blockchains actually very easy for individual validators to manipulate the order of events. And with the increasing complexity of financial applications offered on top of blockchains, this opportunity has finally met its business case. In centralized exchanges, it's already since a long time that traders go through an enormous effort to shave off a millisecond and then turn this into millions. This is what we now see moving into DeFi. And it's only a question of time until validators can make more money by offering reordering than from validator fees. For some, it's already sort of linked. And the other important question is how much revenue do we lose because clients don't want to compete on these terms anymore. So our goal is to design an add-on to existing blockchains that solves this problem by providing fairness, is lightweight enough that we can use it on a high-speed service, and is flexible enough that we can use it with different use cases. And also the Wendy character was really missing from the blockchain space, so now the comic trio is complete. And while it may seem that front-running is a new problem, people have been thinking about this since quite a while. In '94, Mike Reiter and Ken Bierman, both back then at Cornell, defined the concept of causality. So front-running is possible, but not based on the content of a transaction, only based on its existence. When I did my PhD in IBM in 2000, we implemented this in the Sintra toolkit. So this has been around since at least 2002 in a Byzantine context as an implementation. In the same project, fairness was defined in a different way that we talk about it now, more as a stronger version of censorship freeness that also adds a guaranteed bound when a message is delivered. So we can think about this more absolute fairness rather than relative fairness that we talk about now. And what's very common in modern protocol is a rapid leader switch method. So usually there's only one party that defines the order of events, which is the leader. If we switch very fast who the leader is, then an individual party can have only very limited control, and we can put in special protections for the leader. If my agenda is correct, you just listen to a talk on secret leader election, which is one nice way to protect the leader. And finally, most relevantly to us, that's independent parallel work also from Cornell University, which saw the same problems that we do, ran into some of the same impossibilities, and then offered also the protocol that offers block order fairness. The paper is on ePrint. I really recommend you read it. Also, there's a talk from this year's crypto conference where that work is also described, which I can recommend. Now, our model is a relatively straightforward asynchronous Byzantine fault tolerance model. There's a couple of things I want to point out. So one is that Byzantine failures are not very realistic anymore when we also have selfish validators. So I'm currently working on extending the model. The protocols are actually pretty fine with more corruptions as long as they're not coordinated, but it's difficult to find a nice formal model. We do need a known set of validators that can communicate with each other. So for some blockchains that have a very large and very dynamic number of validators, we do need to do a similar approach as Casper did and have a subset of validators do the fairness and then give the result to all the validators for the actual chain. And we have different concepts of fairness and an independent blockchain we interact with, so this also may bring in some modeling aspects. So now we come to what we actually mean by fairness. And as happens a lot in the Byzantine area, if you want to do something, the first thing you run into is an impossibility result. And our impossibility result is that fairness is impossible. A very straightforward definition. If all honest validators see transaction A before transaction B, then we want to schedule A before B actually can lead to an undecidable schedule, and have pointed it out in the table there. Depending on who the bad guy is, you have different orders that you need to enforce, but you don't know it, so you can't decide. So instead of going home, we weaken the definition. So the attempted definition 2 is block order fairness. If all honest validators receive transaction A before transaction B, then A should be scheduled in the same or earlier block than B. And then we do some post-processing that usually manages to get everything ordered appropriately, unless I have undecidable sets. Now, I gave a talk about this, or I mentioned this in a talk in November 2009, and they very naively said protocol is comparatively simple to implement that. One of the reasons why I did think it was relatively simple and now do not think that anymore is that even this definition actually gets us into trouble. And that is when we start to prove termination. Here I take the same block that I've shown before, just spaced out differently. I take a similar block, just upside down, and you can probably guess by the spacing I use. I can now merge them, and now I have those two transactions that are one longer set that needs to be in one block. And I can keep repeating this. And what you see here is that even in a synchronous system, I still can create an infinitely large set of transactions that all needs to end up in the same block, which essentially means I cannot guarantee termination. Now, ways out. The easiest way out is to change our model. The level of network control that an adversary needs to pull off this attack is insane. So if you say, well, we have an adversary that has complete network control, but occasionally makes a little mistake, that's actually enough to break the deadlock there. And interestingly, a lot of other very annoying impossibility results would also go away if we adopt this model. The second approach is pragmatism, which is where we just run a protocol doing block order fairness, and if the block gets too big, we just cut off at a random point, and we have a little bit of unfairness, but everybody can live with this. What we did in the paper is we built a new fairness definition, which does not fall under those impossibility results, and that's timed fairness. Every validator has a local clock, and if there's a time tau, such that all honest parties receive A before tau and B after tau, then A must come before B. That can actually solve fairness, but it's strictly weaker, so that's not good. So what we ended up doing in the paper is a hybrid protocol that runs block order until it runs into trouble with two big blocks, then switches to times fairness to resolve the trouble, and then back to block order. So this finally is Wendy. The protocol as presented here is slightly different from what you have in the paper. It's a bit more cleaner, a bit more tidied up, and hopefully easier to understand. The part you see here is a framework protocol. So this is a part that is independent on the fairness definitions. And the fairness is then defined by two functions, which I describe in the next slide. The first thing that happens here is dissemination. Every validator that sees a transaction attaches a sequence number to the transaction, signs this, and sends this to all potential leaders, which may be all validators, but may also be a smaller set. And that's essentially all that's happening there. So it's one multicast, one message sent. We can do some trade-offs between communication and computation. If we do reliable broadcast, we need fewer signatures, but for now we assume that computation is comparatively cheap. The second big thing that's happening here is computing blocking sets, and that is essentially determining what to do with the transactions. And there's essentially two outcomes for a transaction. So a transaction may be blocked, which means we cannot put it in the next block yet. So then it's held back. Or it can go into the next block, but it may be possible that it has to go together with a set of other transactions, and they are then marked. This is a sets BR, and they are then given to the blockchain as a set. Please take this set and put this in the blockchain together. And then we have communication with the blockchain. So I just mentioned blockchain send is essentially unblocked transactions are given to the blockchain, and blockchain receive, we get a block, we see what transactions have been handled already, so we don't need to process them anymore and can delete them. So this is the two functions that define fairness, blocked and blocked by. Blocked means the transaction may need to get into the same block as a transaction that I haven't seen so far. Since I cannot do this, I cannot put in unseen transactions in there. This transaction has to wait. Blocked by means I'm blocked by a known transaction, so I need to get in the same block as a transaction I've seen already that I can handle with. This is then building the set BR, but if anybody in set BR is blocked and cannot go into the next block, then the entire set cannot go and needs to wait. And I have given an example here on how this looks for block order fairness. The timed fairness is a little bit more complicated, but it's the same principle and the same basic rules. So finally, two features that are important. The first one is that all our transactions have labels. The reason for this is that we have on a multi-purpose blockchain a lot of transactions that are independent of each other, and they shouldn't need to be fair relative to each other. That just costs performance. So I'm only relatively fair to someone with the same label, and different labels can actually use different fairness definitions. And one discussion we are now having is what kind of other fairness definitions are out there, what makes sense, what do traders want, and then every application or market can choose their own fairness. Yes, this is a fairness definition that makes sense on that market. Well, and finally, we have fairness switching that I already described. We have the hybrid protocol that switches the definition of fairness on the fly. We could also think about fairness switching due to other factors such as market behavior. So if I have a market crash, I go to a different fairness definition than I have during normal operation. And in the protocol, this is actually very easy to implement by just switching those two functions from the previous slide and then recomputing all the sets. Finally, a result that hasn't made it into the paper yet, but we got a lot of questions about this. How does Wendy behave in reality? We've actually implemented Wendy by now on a simulated blockchain and simulated network. The main factor is that Wendy delays some transactions to later blocks, and this is primarily caused by votes not having arrived yet. So a transaction is blocked because it can't be processed yet due to lack of votes. And the ratio of transactions that are blocked that way is pretty much exactly the ratio of between message delivery time and the block processing time. So the slower the blockchain, the better for Wendy, relatively speaking. All the other factors are actually relatively small next to this, so we still need to do a bit more systematic work on measuring here. With this, I'm at the end of my presentation. To sum up and remind you of the main results. So fairness, as pretty much everything in Byzantine fault tolerance, comes with its own set of impossibilities. And luckily, there are ways around that we still get satisfactory definitions and protocols. We have a protocol that can support multiple concepts of fairness in parallel, so we can adapt to market needs and circumstances. We have two in the paper, but more are possible. We have a very lightweight protocol, one additional message round, and n-squared communication complexity, which for some blockchains we can optimize down to n. We do have a prototype implementation, so it's not only completely theoretical. We haven't integrated it into real blockchain yet. We don't expect any major roadblocks, but a lot of devils in the detail when the blockchain tries to optimize by itself. And there's still a lot of fun research to do, so if you're interested in this area, let me know and we can have a virtual beer or virtual coffee and talk about other things we can do in this area. And with this, I'm really on the last slide of my presentation. Thank you for listening. I did add links to a couple of resources here. A white paper that has some results that I talked about here, but didn't make it into the conference paper anymore. Link to the Wendy prototype, and next week, Tuesday, I'll have a Q&A if you still have questions left after the session today. And with this, I think if everything goes right, we should meet live now.